compromised capacitor bank within a rotor phase converter will cause a significant current imbalance. To fully understand why this happens, we first have to discuss what a rotor phase converter is and how it operates. A rotor phase converter, also known as a rotary phase converter, is a device used to create three-phase electrical power from a single phase source. This is commonly needed in situations where three-phase power is required for machinery or equipment, but only single-phase power is available from the utility grid. The basic principle of operation involves using a rotating electrical machine, typically an induction motor, along with capacitors, to generate the third phase of power. The induction motor is driven by the single-phase input power, and the capacitors are strategically connected to the motor windings to create a phase shift, thereby generating the third phase. This generated third phase, along with the original two phases from the single-phase input, provides a balanced or near-balanced three-phase output. The capacitor bank is a critical component of the rotor phase converter. These capacitors are carefully selected and arranged to provide the correct amount of capacitance needed to create the proper phase shift and voltage for the generated third phase. The capacitors act as reactive elements, storing and releasing electrical energy to shift the phase angle of the current in the motor windings. This phase shift is essential for creating the 120-degree separation between the three phases, which is characteristic of a balanced three-phase system. When the capacitor bank is compromised, meaning that some of the capacitors have failed, degraded, or are no longer functioning within their specified parameters, the phase shift will be affected. The amount of capacitance will be reduced or altered, leading to an incorrect phase angle for the generated third phase. This, in turn, causes an imbalance in the voltages and currents of the three phases. Instead of having three phases that are 120 degrees apart and have equal or near equal voltage and current magnitudes, the phases will be unevenly spaced and have different voltage and current levels. The consequences of this current imbalance can be significant. Firstly, it can lead to overheating of the rotor phase converter itself. The imbalanced currents cause some windings and components to carry a much larger current than others. This excessive current generates more heat due to the I2R losses, whereas the current and R is the resistance of the windings. Over time, this overheating can damage the insulation of the windings, leading to short circuits and eventual failure of the converter. Secondly, the current imbalance can negatively impact the performance and lifespan of the equipment connected to the rotor phase converter. Three-phase motors, for example, are designed to operate with balanced voltage and current. When the voltage and current are imbalanced, the motor experiences uneven torque production, increased vibration, and higher operating temperatures. This can lead to premature wear and tear on the motor bearings, windings, and other components, ultimately shortening its lifespan. Additionally, the imbalanced current can cause the motor to draw more current than it normally would under balanced conditions, leading to increased energy consumption and higher electricity bills. Thirdly, the imbalanced current can also cause voltage imbalances in the electrical system. This can affect the operation of other equipment connected to the same power source, leading to reduced efficiency, increased wear and tear, and potential malfunctions. Sensitive electronic equipment, such as computers and control systems, are particularly susceptible to voltage imbalances and may experience data corruption or other problems. To mitigate the risks associated with a compromised capacitor bank, it is important to regularly inspect and maintain the rotor phase converter. This includes checking the capacitors for signs of damage such as bulging, leaking, or discoloration. It is also advisable to measure the capacitance of each capacitor to ensure that it is within its specified tolerance. If any capacitors are found to be faulty, they should be replaced immediately with capacitors of the correct type and rating. Furthermore, it is important to monitor the voltage and current balance of the three-phase output of the rotor phase converter. This can be done using a three-phase power analyzer or multimeter. If the voltage or current imbalance exceeds acceptable limits, it is an indication that there may be a problem with the capacitor bank or other components of the converter. In such cases, a thorough inspection and troubleshooting should be performed to identify and correct the issue. In addition to regular maintenance and monitoring, it is also important to ensure that the rotor phase converter is properly sized for the load it is serving. Overloading the converter can cause excessive stress on the capacitor bank and other components, leading to premature failure. It is therefore advisable to choose a converter that has sufficient capacity to handle the maximum load that will be connected to it, with a safety margin to account for future expansion or changes in load requirement. In summary, a compromised capacitor bank in a rotor phase converter can indeed lead to severely imbalanced current. This imbalance can cause overheating, reduced efficiency, and potential damage to connected equipment. Regular inspection, maintenance, and monitoring are essential for preventing and mitigating the risks associated with a compromised capacitor bank. By understanding the role of capacitors in phase conversion and taking appropriate measures to ensure their proper functioning, it is possible to maintain a balanced and reliable three-phase power system. To elaborate on the specific impact of capacitive degradation on the rotor phase converter's output, consider the following detailed points. Firstly, reduced capacitance leads to voltage drop. Capacitors store electrical energy, and their ability to do so is quantified by their capacitance value, measured in microfarads. If a capacitor's capacitance decreases due to aging or failure, it can no longer store as much energy. In the context of a rotor phase converter, this means the voltage generated in the manufactured phase will be lower than intended. This voltage drop isn't uniform, it varies with the load on the system. Under light load, the voltage drop might be minimal, but as the load increases, the voltage sags more significantly, leading to an imbalanced voltage profile across the three phases. Secondly, phase angle distortion occurs. Ideal three-phase power has each phase separated by 120 electrical degrees. Capacitors are instrumental in creating this phase shift in a rotor phase converter. When a capacitor degrades, it not only affects the voltage magnitude but also alters the phase angle. Instead of a perfect 120-degree separation, the phases might be shifted by, for example, 110 or 130 degrees. This phase angle distortion exacerbates current imbalance because the connected three-phase loads are designed to operate with a specific phase relationship. Any deviation from this ideal can cause excessive current draw in one or more phases. Thirdly, harmonic distortion increases. Beyond the fundamental frequency of the power system, usually 60 Hz, there are harmonic frequencies that can distort the voltage and current waveforms. Capacitors help filter out these harmonics, providing a cleaner power supply. When the capacitor bank is compromised, its ability to filter harmonics diminishes. The increased harmonic content can lead to a variety of problems, including overheating of transformers and motors, interference with sensitive electronic equipment, and inaccurate meter readings. Furthermore, resonance can occur. In electrical circuits containing both inductors and capacitors, resonance can occur at a specific frequency where the inductive reactance and capacitive reactance cancel each other out. This can lead to very high currents and voltages in the circuit. A compromised capacitor bank can shift the resonant frequency, potentially causing it to coincide with the harmonic frequency present in the system. This resonance amplifies the harmonic, leading to even greater distortion and potential equipment damage. Fifthly, overheating and premature failure occur. The imbalanced currents caused by a compromised capacitor bank create excessive heat in the rotor phase converter and connected equipment, particularly motors. This heat degrades insulation materials, reduces the lifespan of components, and increases the risk of failure. Motors operating under imbalanced conditions also experience increased vibration and mechanical stress, further contributing to premature wear and tear. Sixthly, inefficiency and increased energy consumption result. Three-phase equipment operates most efficiently when the voltage and current are balanced. Imbalances force equipment to work harder to produce the same output, resulting in higher energy consumption and increased operating costs. The wasted energy is dissipated as heat, further exacerbating the problems associated with overheating. Seventhly, nuisance tripping of circuit breakers can occur. Imbalanced currents can trigger protective devices like circuit breakers, causing them to trip unnecessarily. This can disrupt operations and create downtime, especially in critical applications. Nuisance tripping can also mask underlying problems, making it more difficult to diagnose and resolve the root cause of the imbalance. Eighthly, motor control problems arise. Variable frequency drives, or VFD, are often used to control the speed and torque of three-phase motors. These drives are sensitive to voltage and current imbalances. A compromised capacitor bank can cause VFD to malfunction, leading to erratic motor behavior, reduced performance, and potential damage to the drive itself. Ninthly, power factor correction is negatively affected. Capacitors are often used to improve the power factor of electrical systems, which is a measure of how efficiently electrical power is used. A compromised capacitor bank reduces its ability to correct the power factor, leading to increased reactive power and higher utility bills. A low power factor can also strain the electrical grid, causing voltage drops and other problems. And finally, equipment damage and safety hazards are elevated. The combination of overheating, vibration, and voltage stress caused by a compromised capacitor bank can lead to catastrophic equipment failures. These failures can pose safety hazards to personnel and property, including electrical shocks, fires, and explosions. Prompt detection and correction of capacitor bank problems are essential for preventing these hazards. Therefore, regular maintenance practices for Roto phase converters include visual inspections of the capacitors for signs of bulging, cracking, or leaking. Capacitance measurements should be taken periodically using a capacitance meter to verify that the capacitors are within their specified tolerance. Insulation resistance tests can also be performed to check for insulation breakdown, which can indicate a failing capacitor. Additionally, monitoring the voltage and current balance of the three-phase output is crucial. A three-phase power analyzer can be used to measure voltage and current imbalances, harmonic distortion, and power factor. These measurements can provide valuable insights into the health of the capacitor bank and the overall performance of the Roto phase converter. When replacing capacitors, it is essential to use the correct type and rating. Capacitors are available in a variety of types, including electrolytic, film, and ceramic capacitors. Each type has its own characteristics and is suitable for different applications. Using the wrong type of capacitor can lead to premature failure and performance problems. The voltage and capacitance ratings of the replacement capacitors must also match the original specifications. Using capacitors with low ratings can result in overheating and failure, while using capacitors with higher ratings can lead to overvoltage problems. Remember to adhere to proper safety procedures when working with electrical equipment. Always disconnect the power before performing any maintenance or repairs. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electrical equipment, consult a qualified electrician. Regular maintenance and monitoring of the capacitor bank are essential for ensuring the reliable and efficient operation of a Roto phase converter. By detecting and correcting problems early, you can prevent costly equipment failures, reduce energy consumption, and improve the overall safety of the electrical system.